Next, let me give you a brief introduction of dynamics. So let's first take a look at a simple spring mass system, where a mass M is supported by a spring, whose spring constant is K. And the origin of this x-axis is chosen as the balance position of the mass centroid. Then a displacement of the mass from its balance position causes a recovery force F is equal to negative Kx. Right, this is the Hooke's law. Right, we pull this mass away from its balance position with a distance x. Then the recovering force generated by the spring is equal to negative Kx. Then if we release the pull mass, what will happen? We pull away this mass from its original position, from its balance position, then release it. What will happen? Let's answer this question using Newton's second law. Right, namely, we can establish a motion equation based on Newton's second law. And namely, F equal to, or ma is equal to F. Right, this is the Newton's second law. And the ma, the acceleration, is the second derivative of x, the displacement, with respect to t. Right, the force is equal to negative Kx. Right, the only force applied to the mass is the spring force, the recovering spring force. Right, that's the reason we have the negative sign here. Here we neglect the gravity. Right, we only consider the spring force. Now we can divide, or we can move m to the right side. So the second derivative of x with respect to t is equal to negative k over m times the x. The general solution of this equation is a sinusoidal function, right? Xt, right? X, the position. The displacement is a function of time. Right? It's equal to a sine square k over m t plus alpha. A is the amplitude of vibration. Alpha is a phase lag, right? This alpha is phase lag. And the square root of k over m is called natural frequency, and typically denoted as omega 0. Omega 0 is also called undamped resonant frequency. So from this result, we can see that after we release the pull mass, the mass will oscillate around the origin with a frequency omega 0. Its displacement is a sinusoidal function. So this is the oscillation, and the oscillation frequency is omega 0, square root of k over m. And here we are actually discussing an ideal case. And we assume there's no friction, right? So this oscillation will actually will forever, right? It will oscillate forever. Right? Its amplitude will not decay. Right? Obviously, this is an ideal case. Let's consider a more general case. Here we add a damper, a damping element, which account for friction. And we also add an external force, Fex. with a damping element and an external force, then the motion equation or the governing equation is Fex minus B dx dt. Please note that the second term represents the friction force. Dx dt is the velocity, right? Dx dt is the velocity. This damping force is typically proportional to velocity. Right? The examples include air friction and the internal friction of the spring. Right? They are both proportional to velocity. So this is a friction force, a damping force. This minus sign means this force is always opposite to the velocity, right? Dx dt. And then minus kx, right? This is a spring force. So now the left side of the equation is a net force. The net force experienced by the proof mass. Right? So again, this is based on Newton's second law. Right? F is equal to ma. Right? Ma. Right, next, we move the terms with x to the right side. So left side is only Fex, the external force. The right side we have m, right, times the second derivative of x with respect to t, plus b, where b is a damping coefficient, right? B times dx dt, the velocity, plus kx, the x displacement, k the spring constant. So x is the displacement, m the mass, b the damping coefficient, k spring constant, F is the external force applied. And this second order differential equation can be solved using Laplace transform. I believe all of you have learned Laplace transform. Right? We can perform Laplace transform on both sides of this second order differential equation. Right? Then the force, right, Fex in time domain becomes a capital F. Right? This S is a complex frequency, so it's converted to, it's transformed to frequency domain or S domain. Right? So left side becomes Fs. The right side is a ms squared. Right? The second derivative becomes s squared, and xs, right? X capital X s is a Laplace transform of the displacement in time domain. Plus bs xs, right? This s comes from the first derivative, right? Dx dt becomes the s times the x, right? And plus kx. So we replaced integration or differentiation with a multiplication, right? Second derivative becomes s squared, right? First derivative is just s. So the analysis of the second order differential equation is simplified. Then we define a force to displacement transfer function, right? Hs. Hs is defined as xs over fs. Right? Fs is the force we apply to the spring mass system. So it's an input. Xs is the output, right? The displacement, the result of the applied force. Right? So this is a transfer function that gives you the relationship between output and the input. Right? Then from this equation, this transfer function can be easily derived, right? Which is equal to 1 over ms squared plus bs plus k. And we can divide both top side and bottom side, numerator and the denominator with m, right? So the transfer function becomes 1 over m over s squared plus b over m s plus k over m. So that's a transfer function of this spring mass system in S domain. Next, let me introduce a very important parameter, the quality factor, right? Q factor. The quality factor Q of a damped oscillator is defined as a 2 pi energy stored per cycle over energy lost per cycle. And it can be derived that it's equal to omega 0, the natural frequency, times m over b, by mass over damping coefficient. And the omega naught is the square root of k over m, right? Omega naught, omega 0 is the square root of k over m. So we can replace omega 0. So q is equal to km over b squared, square root. And with this quality factor, the transfer function can be expressed by this new form. Right? We replaced the b, right? In the previous equation, we have b here. But now actually we can replace the b with a quality factor. So now the transfer function is a function of quality factor. 1 over m divided by s squared plus omega 0 over q times s plus omega 0 squared. It's more widely used here. Okay, q is more widely used, right? Because we can measure q in a much easier way than damping coefficient b. Right, so this form is a more widely used for the transfer function. Please note that this transfer function is a complex function, right? It's a complex function. S is a complex number. And then we can calculate the amplitude response by calculating the amplitude of this transfer function. And we also need to replace S with j omega. So we replace S with j omega. J omega squared becomes the negative omega squared, right, plus omega 0 over q j omega plus omega 0 squared. And we want to calculate the amplitude of this complex number. Then it's simply equal to the square root of the real part, right? Real part squared plus this imaginary part squared. Right? That's how we calculate the amplitude of the complex number. Right? So this is the amplitude response of the spin mass system. Right? We can say it's a function of omega. Right? At a different frequency, the response will be different. And the phase response can be calculated as well based on this transfer function. Right? The theta is equal to arc tangent, the imaginary part, like omega 0 over q times omega, imaginary part divided by the real part. This gives us the phase response. But if we know the amplitude response and the phase response, then we can calculate the displacement x if we know the external force applied. I assume this external force is a b sine omega t, right? It's a sinusoidal force. Then the resulting displacement, right? The force applied can be considered as an input. The displacement can be considered as a output. So we can consider this spin mass system as a black box. Input is a F, output is a xt, right? And we know it's amplitude response and phase response. Then xt is simply equal to the phase response times B, right, the amplitude of force, then times the sine omega t plus theta, right? Theta is just a phase response. So we can calculate the output or the displacement, right, if we know the phase response and the amplitude response. Right? That's also how we use the amplitude and the phase response. In the last lecture, we discussed this spring mass system with a damping element and an external force, Fex. But then we defined a force to displacement transfer function, H, HS. HS defined as a X over F. Right? X is a displacement, right, which is considered as an output. F is a force, right, so it's considered as an input. Right, this transfer function, right, for this spring mass system can be derived, right, based on Laplace transform. Right, then we introduced the quality factor Q. This is a very important parameter of damped oscillator. It's defined as a 2 pi energy stored per cycle over energy lost per cycle. So that's a parameter that describes how lossless the oscillator is. Right? If the oscillator has a very small energy loss, then we can say its quality factor Q is very large, right? Because it's inversely proportional to the energy lost per cycle. Right, so actually it's inversely proportional to B, which is a damping coefficient. But then we derived amplitude response and the phase response, right, theta, right, from the transfer function. Right, transfer function is a complex function, right? So we can calculate its amplitude and the phase. Right? Both of them are functions of omega. Right? Omega is the frequency of the input force, the external force applied. So we can assume the external force Fex is a B sine omega t. Right? This omega is this omega, the frequency. But then the displacement of the mass xt can be calculated based on amplitude response and the phase response. Right? Specifically, xt is equal to the amplitude response times B times sine omega t plus theta. Right? Theta is the phase response. Right? Please note that this is how you solve problem 1 of the homework. Questions? Let me say a few more words about the amplitude response and the phase response of the spring mass system. When omega is much smaller than omega 0, right? Please note that omega is the frequency of the external force. Omega 0 is the natural frequency or resonant frequency. Right, omega 0 is equal to square root of k over m. That's something we introduced previously. Right, when this omega is much smaller than the resonant frequency of the system, right? So for example, okay, for simplicity, let's just assume omega is 0, right? Then this is a negligible. Omega is 0. This is also negligible. Okay. So the transfer function, the amplitude response of the transfer function is approximately equal to 1 over m divided by omega 0 squared. And omega 0 is equal to square root of k over m. Squared is k over m, right? So it's divided by k over m. M cancel with each other. So the amplitude response is simply equal to 1 over k. Right? When the frequency is very low, a low frequency or 0 frequency. And the theta, the amplitude, the phase response, right, is equal to, when omega is equal to 0, right, this theta is equal to negative arctangent 0, right? Omega is equal to 0. Then theta is approximately equal to 0 degree. That means the displacement, right, the output of system displacement is in phase with the force applied. Right, so this is actually what we expected. Right? When the frequency is very low, the displacement is in phase with the force applied. In addition, I want to point out that the H, the transfer function. Let me erase this first. The transfer function H is defined as x displacement over f, right? And this is equal to 1 over k. So x or f, okay, let's only consider the magnitude, is equal to kx. Right? F is equal to kx. This is simply what? The Hooke's law, right? So at low frequency, the response of the spring mass system can be described using Hooke's law, right? F is equal to kx. And when omega is equal to omega 0, right? When the frequency of the force applied is equal to the random frequency of the system, right? The two frequencies match, then the amplitude response will be equal to right. Then we simply replace omega with omega 0, right? So then omega 0 square minus omega 0 square is 0. And this omega becomes the omega 0. So omega 0 square divided by q. Then this q can be flipped up to the top, right? So become the q over m divided by omega 0 square. So it's equal to q over k. So we can say that at the random frequency, the amplitude response is q times its low frequency response, right? Q over k, right? This is 1 over k. And the phase response, right? We replace omega with omega 0, omega with omega 0. So theta is equal to arctangent infinity, right? Because this is 0, so it's infinity, right? Which gives us negative 90 degree. So the phase difference between the output and the input is a negative 90 degree. But we know that Q, the quality factor, Q is a measure of how lossless the oscillator is. When Q is greater than 1 over 2, right, 0.5, the system is underdamped. The high Q, high quality factor means that first, the amplitude response of the transfer function has a sharp peak around its natural frequency, right, as shown in this figure. Right? It has a sharp peak around omega 0. Right? Please note this figure plots the amplitude response. Right? Horizontal axis is the omega, vertical axis is the amplitude response. Right? Specifically, when omega is equal to omega 0, the amplitude response is equal to Q times its low frequency response. Right? We just mentioned, right? It's Q over K. Low frequency response is 1 over K. So the factor of Q. Right? For example, if Q is 1000, then this peak, okay, we have an amplitude 1000 times of its low frequency response. So very sharp peak. And the high Q also means a sharp transition from 0 degree to negative 180 degree for phase response around its natural frequency. Right. So this curve, okay, this solid line represents the phase response of a high Q system, okay? A very sharp transition from 0 degree to negative 180 degree. Okay. Negative 180 basically means the input and the output are out of phase. Their phases are opposite. Right? 0 degree in phase. Right? They have the same phase. So this is a high Q system or underdamped system. Now when Q is equal to 1 over 2, the transfer function HS has 2 identical poles, and the system is said to be critically damped. Right? For this critical damped case, there is no peak, right? Because Q is equal to 1 over 2, right? So it's actually lower than its low frequency response, right? No peak around omega 0. And when Q is less than 1 over 2, the system is overdamped. And its amplitude response, right, starts to fall far below omega 0. So this bottom dashed line represents the amplitude response of an overdamped system, right, whose Q is less than 0.5. Right, this curve in the middle represents the critically damped case. Right? So this is the underdamped, critical damped, and overdamped. Okay, or high Q, Q of 0.5, Q less than 0.5. Right, the concept of underdamping, critical damping, and overdamping can also be explained in time domain. I pretty know that in the in previous figures, the horizontal axis is omega, the angular frequency. So this is these two descriptions in frequency domain. Now let's describe underdamping, critical damping, overdamping in time domain. So in this figure, the horizontal axis is time. Let me write down. The horizontal axis is time. So please do not be confused. One is a time domain description, another is a frequency domain description. Let's first discuss the undamped case. This is actually the ideal case, whose Q is infinity, right? Infinitely large, right? Because no energy loss. So Q is very large, right? Ideally infinity. The system oscillates at its natural frequency or natural random frequency omega 0 with a constant amplitude. So thus, this pink curve, a pink waveform, represents the undamped case. Right, the system will oscillate with a constant amplitude forever. Right, no energy loss. So this oscillation will last forever, ideally. Underdamped case, right, Q is greater than 1/2. The system oscillates with the amplitude gradually decreasing to 0. High Q system can oscillate or resonate for a long period of time once energized. So this blue waveform represents the underdamped case, or a high Q oscillator, high quality factor oscillator. Critically damped case, Q is equal to 1/2. The system returns to equilibrium as quickly as possible without oscillating. Right, so you can imagine now you place the oscillator into a very viscous medium, right? For example, oil. Right? Then the pool mass returns to equilibrium without oscillating, without passing the equilibrium point by 0. So this is a critically damped case. Right? This green line represents the critically damped case. Right? Green line. Let me mark it. This one, Q is 1/2. Right? Critically damped. Overdamped case, right? Q is less than 1/2. The system returns to equilibrium without oscillating, right? Similar to critically damped case. Smaller values of Q return to equilibrium more slowly. So it's slower than the critically damped case. Then we know that this color is probably red. Okay, this red curve represents a case whose Q is less than 1/2. Right? It returns to 0 more slowly than this green curve. Right, so that's the overdamped case. Questions? So we know that RMA testers increase. So please make sure you understand this concept quite clearly. I pretty know that the quality factor, right, Q, right, is inversely proportional to B. Right, B is a damping coefficient, and an important source of damping is the air friction. Right, therefore, to reduce air damping, right, vacuum package is necessary. So we can package the oscillator in vacuum to increase the quality factor. And some of you probably know that some oscillators, such as a quartz tuning fork, right, it's packaged in vacuum. Right, for other applications, damping is introduced intentionally to reduce the quality factor. Right? So there are some applications which may need a smaller Q. Examples, right? Some examples of the spring mass system, or examples of oscillators. Let's first take a look at the natural frequency of a cantilever beam with a concentrated end mass. And for this example, we assume that the mass of the beam is neglected. Right? We only consider the mass of the mass attached to the tip, not the cantilever itself. But in addition, the dimension of the end mass is neglected. So we assume this is a point mass. Right? So the force generated is a point force. Right? Let's derive its natural frequency, omega 0 or omega naught. And from our previous discussion, right, we learned that the natural frequency of a spring mass system is equal to square root K over M. Please note that this cantilever beam with a concentrated end mass can be modeled as a spring mass system. Right? This mass and this cantilever serves as a spring. Right? So this is a spring mass system. Right? Then we can calculate its natural frequency by square root K over M. Right? M is simply the mass. So we only need to find the spring constant K. How do we find the spring constant of this cantilever beam? Recall that the displacement caused by a concentrated force F acting on the end of the cantilever beam has been calculated previously. We calculated this displacement in this slide, right? A point force F applied to a tip. Then we found its a displacement W as a function of X. Then its a tip displacement, or the maximum displacement, can be calculated by setting X to L. Right? So we can calculate its tip displacement. And its tip displacement is L cubed over 3EI times F. Right? So it's a linear function of F, right? Proportional to F. F is force applied. So this is a linear spring. Then we can define or calculate the spring constant. We know that I is equal to, or in case you forgot, I is equal to 1 over 12 WH cube. Right? H is a thickness, and the W is a width. Okay. So I is 1 over 12 WH cubed. So this is a tip displacement. Then the equivalent spring constant K can be calculated based on Hooke's law. Right? From Hooke's law, we know F is equal to Kx. Okay, let's neglect the sign. So K is equal to F over X. Right? So K is equal to F over X. X the displacement, tip displacement. So here is the WL. Right? We just substitute WL into this expression. So finally, K is equal to E, right, Young's modulus, WH cubed over 4L cubit. Right, so it's proportional to W, proportional to the cubit of thickness. Right, so if you double the thickness, right, its spring constant is increased by a factor of 8, and it's inversely proportional to L, the length cubit. Okay, L is the length. Let's leave it here. So finally, omega 0, the natural frequency, is equal to square root EW H cubit over 4L cubit M. So it's inversely proportional to square root of M, the mass. Questions? Now we can say that if we increase the mass, right, the random frequency decreases. This omega 0 is a function of mass. 2.2.2, natural frequency of a cantilever beam with evenly distributed mass. Right, let's consider the mass of the cantilever itself. But then we can say if we assume this cantilever beam has a uniform cross section, then its mass is also evenly distributed. So let's calculate the natural frequency of such a cantilever beam. Right, that's is different from the previous example. In the previous case, the mass is concentrated at the tip. Now it's distributed, evenly distributed. Then we cannot use the concentrated mass model anymore. We have to use other methods, such as Rayleigh's method, which is an energy method, to calculate omega 0. Well, I will skip the details and give you the result here directly. Omega 0 is equal to 1.019 H over L squared, square root E over rho. Please note that there's a rho here is the density of the mass of the cantilever beam material. Or if we assume mass is concentrated at the tip, we can replace the rho with its mass. Then the effective mass is about 24% of M. So 0.24 times M. Next, 2.2.3, natural frequency of a double clamped beam with an evenly distributed mass. This is a cantilever beam. One end is fixed, the other end is free. Now both ends are fixed. So we call this a double clamped beam or a bridge. Then its resonant frequency or natural frequency is equal to 6.48 H over L squared, square root E over rho. Then we can compare this result with the previous case. And we can see that this double clamped beam has a higher resonant frequency. Right? Omega 0 is larger than that of cantilever beam. Right? This is not surprising, right? Because a double clamped beam is much stiffer than a singly clamped beam or a cantilever beam. Right? So its natural frequency is larger. And from above discussions, we can observe that the mass change M or density change rho can lead to resonant frequency change. Right? Rho or mass change may lead to the change of omega 0. Right? This is the operation principle of resonant mass sensor. By the way, please know that omega 0 is the angular frequency. If we are talking about the real frequency, f, right? F 0 is equal to omega 0 divided by 2 pi. So when you work on your homework, right, please pay attention to this difference, right? F is equal to omega divided by 2 pi. So this is the operation principle of resonant mass sensing, where we can detect mass change or density change by monitoring the resonant frequency change, right? The change of omega 0 or F0. Right, based on this principle, Atto-gram detection using resonating cantilevers has been demonstrated by researchers from Cornell University. Please know that 1 atto-gram is equal to 10 to the power of negative 18 gram. So atto is 10 to the power of negative 18. Pico is 10 to the power negative 12. Femto, negative 15. Right? Atto, negative 18. So very small number. And this is 1 atto-gram is a mass of a single 1 kilo base pair DNA molecule. So this DNA molecule weighs 1 atto-gram. Right? So this is a very, very small mass. This SEM image shows a 4 micron long silicon cantilever. Right? This silicon cantilever is a 4 micron long. There is a gold dot fabricated on the tip of the cantilever. This figure plots the frequency responses before and after the adsorption of alkene cell molecules. I know that alkene cell molecules adsorb to the gold surface. When they adsorb to the gold surface, the mass, what happened to the mass? The mass increases, right? The mass of the cantilever increases. Then what will happen to its resonant frequency, right? F0? It will decrease, right? So then we can see that in this figure, the solid line represents the frequency response before the adsorption. Right? Its resonant frequency is higher. The dashed line, right, represents the frequency response after the adsorption, right, whose resonant frequency is lower. So when mass increases, resonant frequency decreases. And in this work, a mass resolution of 0.39 atto-gram has been demonstrated, right, for a 4 micron long cantilever. Right? This is a very impressive work. This technique, right, presents an opportunity for detection of a single large biomolecule. But please know that the resonant frequency of double clamped beam is a function of the axial force applied. In previous case, we actually assume the force, the axial force is 0. When an axial force N is applied, its resonant frequency is equal to omega 0, 0. Right? This is the resonant frequency when the axial force is 0, right? No force applied. Times square root 1 plus gamma. Gamma is a constant, right? 0.2924. N, that's the force applied. L squared over 12 EI. E is the Young's modulus. I is the moment of inertia, which is equal to 1 over 12 times the WH cubic. So we can see, right, the resonant frequency, omega 0 or F0, is a function of N, right, the axial force applied. Right, this is the operating principle of resonant force sensor or string gauge. Actually, right, this is analogous to tuning the strings of piano, guitar, or violin. If you have ever played those instruments, you should know this very well. You can adjust the tone by changing the tensile force. Typically, when we increase the tensile force, the tone will increase. Right? Its resonant frequency will increase. So this is actually the kind of principle we already use a lot in our everyday life. And this principle has also been used for force sensing and mechanical string sensing. So used for resonant force sensor or string gauge. One example, resonant beam pressure sensor. As shown in this figure, right, resonant beam, this beam, resonant beam is fabricated on the surface of a flexible diaphragm. When a pressure is applied from the top, for example, the diaphragm deflects. Then the beam is stressed. Then the resonant frequency will change. As we learned here, it's a resonant frequency is a function of the axial force applied. So pressure in this example, the pressure leads to change of resonant frequency. Right, so we can measure the pressure by monitoring the shift of resonant frequency. Note that the measurement of frequency is one of the most robust and accurate methods available. In some sense, it's easier to measure frequency than current or voltage. And this figure plots the resonant frequency as a function of pressure applied. And they claim that accuracy of 0.01% has been achieved. The bending behavior of diaphragm is of crucial importance for pressure sensor design. So let's consider a circular diaphragm with a uniform loading. I know that here we assume small deflection. The deflection of the diaphragm W, is less than 0.2 times H. H is a thickness of the diaphragm. Then the deflection of the diaphragm, W, right? W is the deflection. As a function of radius r, right? R is the distance to the center of the diaphragm under pressure P. It is given by this equation. Right? WR is equal to P. Okay, P is the pressure applied. Right? So the deflection is proportional to the pressure. Right? A is the diameter. Sorry, radius of the diaphragm. Right? 2A is the diameter. D, right? D is the bending rigidity of the plate, right? Which is equal to EH cubed divided by 12 1 minus nu square. Right? E is the Young's modulus. H is the thickness, right? Diaphragm thickness. Nu is the Poisson's ratio of the plate material. The maximum deflection, right? Please note that this displacement is a function of r. Obviously, it's a function of r, right? Distance to the center of the diaphragm. Where is the maximum displacement? Very simple. It should occur at the center, right? Mathematically, we can also tell from this equation, right? R, when R is equal to 0, right? This is R over A square. So when R is equal to 0, WR is maximized. So W max is equal to P A to the power 4th over 64D. That is the maximum displacement of the diaphragm, which occurs at the center. Occurs when R is equal to 0. Right? D, again, D is just a bending rigidity. Next, let's discuss the stress distribution qualitatively. But first, we can observe that, as shown in this figure, the stress is proportional to the distance from the neutral plane. The center plane is the neutral plane. This is a dashed line. On neutral plane, there is no stress, and the stress is proportional to the distance from the neutral plane. Right, so we can see that the maximum stress occurs on the surface, either top surface or bottom surface. Right, this is something we learned in the beam theory, right, in chapter 9. Right. It's a similar. Maximum stress occurs on the surface. Then we can conclude that the piezo resistors, right, should be placed on the surface of diaphragm in order to sense the stress, or in order to maximize the sensitivity. Right, the piezo resistors or strain gauges should be placed on the surface, either top surface or bottom surface, not embedded in the middle or embedded inside the diaphragm. It should be placed on the surface. So that's a very important conclusion. Second, the surface stress. Surface stress is change signs along the radial direction. From the edge to the center, the surface stresses change signs. And for this deflected diaphragm shown here, we can see, let's focus on top surface. We can see the top surface stress is a tensile at the edge, right? This is the edge. And when you move to the center, we can see the stress become compressive. Right? The top surface now is compressive. At the edge, the top surface is stretched. At the center, the top surface is compressed. So I think this is a kind of intuition where you can actually visualize that. Okay, and it's in some sense, that's a common sense in everyday life. And this figure plots the stress as a function of position. I know that horizontal axis is R over A. Right? We plot both longitudinal stress and the transverse stress. That this is the center, this is the edge, right? This is 0, right? This is R equal to A is 1, right? R is 0 is right here. So this is center, this is the edge of the diaphragm. Then we can observe that the maximum longitudinal stress, surface stress, okay, not the internal stress. The maximum longitudinal surface stress, sigma L, occurs at the edge of the diaphragm. Occurs at this point, not center, right? Edge has a larger stress. And at about 1/3 of radius, longitudinal stress changes signs. This distance is about 1/3. 1/3 of radius. Right? Within this distance, the longitudinal stress is a positive. Right? Beyond this distance, it becomes negative. Right? So based on those two observations, right, we can conclude that, right, for a circular diaphragm, the piezo resistors is better to be placed on the edge, right, because edge has a larger stress, and the length of the piezo resistor need to be less than 1/3 of the radius. Right? Otherwise, your sensitivity will be reduced. Right? It's a negative stress. The sensitivity will be reduced by this negative stress. And then the maximum stress occurs at occurring at the edge is approximately equal to 0.75, right? Actually, 3/4, right? 0.75 times the P A square H square, right? P is the pressure, A is a radius, right? This distance. H is a thickness, right? Thickness of diaphragm given here, H and A. So there's a maximum stress is proportional to pressure, proportional to A squared, and inversely proportional to H squared. Right, so if we double A, the maximum stress will be increased by a factor 4. And if we increase H, the maximum stress will be decreased. Questions? Stress distribution of square diaphragm. We just discussed the stress distribution on circular diaphragm. Now let's discuss the case of square diaphragm. But this is a square diaphragm with an edge length of 2A. Right? We know that this distance is 2A. Right? This distance is 2A, not A, 2A. Then, right, it can be derived that the deflection W as a function of X and Y. Right? Here we use a XY coordinate. The origin is selected at the center. WXY is equal to this, right? 1/47 P pressure. A is a half of the edge length. Right? We know that A is not the edge length; it's only half of the edge length. D, the bending rigidity, right? We introduced previously. Right here, bending rigidity. Right. D equal to this. Right. X, Y are the positions. Okay. A is a half of the edge length. Where is the maximum deflection? Very simple. Right at the center, right at the origin, when X, Y are both equal to 0. So W 0, 0 is the maximum displacement. Maximum deflection. Right, so we make X equal to 0, Y equal to 0, then the maximum displacement is simply 1/47 P A to the power 4th over D. So that's the maximum displacement of the square diaphragm. And the maximum stress, the maximum x stress, or stress along x direction, occurs at just two locations. Center of the edge, right? The sigma x, right? Stress along x direction. And the maximum y stress occur at these two, sigma y. So it's symmetric, right? Sigma x, sigma y, sigma y. And the maximum stress is equal to approximately 1.01, right? It's about equal to 1. P A squared over H squared. So that's the maximum stress on a square diaphragm. Right, these two figures, right, plot the distribution of sigma x and the sigma y on a square diaphragm. Now you can see the maximum sigma x occur at these two locations, right? Name these two. Okay. And the maximum sigma y occur at these two locations, right? The center of these two edges. Question. Let's compare a square diaphragm with an edge length of 2a and a circular diaphragm with a diameter of 2a. Okay, two diaphragms. One the square one with an edge length of 2a. Another is a, okay, let me draw one. A circular one. Let me choose a different ink. Okay, a circular diaphragm with a 2a. Which one has a larger maximum deflection and maximum surface stress? So let's first take a look at the square one. Right, the square one, the maximum deflection is 1/47 PA to the power 4 over D. How large is maximum deflection of a circular diaphragm with a diameter 2a? Right here, PA to the power 4 over 64 over D. One is 1/47, another is 1/60. So which one has a larger maximum deflection? Which one? Why the square one, right? Square one is 1/47. The circular one is 1/60. The square one has a larger deflection. How about the maximum stress? For square one, it's 1.02 PA squared over H squared. How large is the maximum stress for surface stress, right? For the circular one, 0.75 times PA squared over H squared. So which one has a larger stress? The square one. Again, the square one, right? 1.02. That is the 0.75. But this is actually very easy to understand. Right? Since a square diaphragm with an edge length of 2a is larger than a circular diaphragm with a diameter of 2a. Right? The square diaphragm has a larger area, so the square diaphragm is more flexible. Right? Does this make sense? So the square diaphragm has a larger deflection and a larger surface stress. It's more flexible.
Examples of sensors based on diaphragms. The first example is a pressure sensor, as schematically shown in this figure. The external pressure causes the deflection of the diaphragm, which can be subsequently measured by various sensing mechanisms. The pressure range of the pressure sensor. The pressure range, or the maximum pressure that can be applied to the diaphragm, is determined by the maximum stress the material can sustain. Namely, sigma max should be less than sigma yield. Right? Sigma yield is a yield stress or yield strength. And this table summarizes the yield stress of a number of common materials. The maximum stress of a square diaphragm occurs at plus minus A, 0, right? Namely at the centers of the edges. Sigma max is approximately equal to 1.02 P A squared over H squared. This maximum stress should be less than the yield stress of the material, of the diaphragm material. Like for example, if we choose a silicon, right, then the yield stress is 7,000 megapascal. Right? This is equal to 7,000 megapascal. Right? Right. Then we can calculate the P, right, which is the pressure range based on this inequality. Another example is a microphone, which detects sounds, right, namely acoustic waves or pressure waves. The sensing element of a microphone is still a flexible diaphragm, which converts the impinging acoustic waves into mechanical displacement or mechanical vibration. And a backplate, acoustic holes, and a back chamber are used to tune the frequency response of the microphone. And this pressure equalization port allows the pressure inside the chamber to be equalized with the ambient pressure outside, and thus prevents DC drift, right? Prevent the DC drift of the microphone. Right. Therefore, microphones are leaky pressure sensors, right, in some sense. Right. These two sensors have similar structures. And the desirable frequency range for microphones is typically from 20 Hertz to 20 kilohertz. Natural frequency of diaphragms. Right, for a circular diaphragm, right, whose diameter is about 2A, the natural frequency of the fundamental mode, right, omega 0, is equal to 40.8 H over 2A squared times the square root E over 12 1 minus nu squared rho. H is a thickness, right? 2A is a diameter. E is a Young's modulus of the diaphragm material. This nu is a Poisson's ratio. Rho is the density of the diaphragm material. For a square diaphragm, whose dimension is 2A by 2A, the natural frequency, omega 0, is 35.16 H over 2A squared times the square root. We can observe that the natural frequency of a circular diaphragm with a diameter of 2a is greater than that of a square diaphragm with a dimension of 2a by 2a. This is actually expected, since we know that this circular diaphragm is more rigid than the square diaphragm, whose dimension is 2a by 2a. So this is actually what we expected. We can see 40.8 is greater than 35.16.